Hi everybody, I am Matteo Collina, co-founder and CTO of Platformatic, and today we are going to talk about the Node.js event loop, or more specifically, what does it mean to not trash the event loop. So we're talking about Node.js, right? This applies also to other libraries that have the event loop pattern, so you can use this with almost whatever you want. This concept with whatever other system you want. But this is actually important to note that these kind of behaviors are inherited on event loop based systems, okay? And, you need to consider them, essentially. They are also part of what a real-time system is, or a pseudo real-time system works. So there is a lot of math, to be honest, if you want to go into this word. So, okay. Let's start talking about the I/O event queue and how Node.js works. So you have your Node.js when it's running, okay, it runs its JavaScript and it's C++. Okay, when it runs synchronously. Or whenever it runs code, it's synchronously run. Okay, meaning that we are not accepting any new event while other code is running. And once then, what does it do? Well, typically when you execute some code, it's go and schedule some work to do on the kernel. And then after it's done, it send an events back to the event queue. It's great, okay? So, but how does that mean? How does that work? Well, let's get into details, okay? So this diagram was done by my ex-colleague James Nell before. I've simplified this a little bit. So the event loop, when the event loop is waiting for it accepting new I/O, is accepting new events, is not executing anything, okay? It's just waiting. And when it's executing something, it kicks in some C++, C-C++ code, and then that kicks in some JavaScript. Typically, when this happens, is not accepting any new event, okay? It's just executing things. It's just executing the code. So, and this is great, okay? Because this means that our CPU can process a lot of things, like 10,000 requests per second, 20,000 requests per second, okay? On concurrently, sorry, not on a single processor, on a single CPU, because it doesn't have to wait for each one of them. This model, it's way more performant than the thread-based model, mostly because thread costs a lot of memory to execute for the kernel. So, okay, great. What is the normal flow of an HTTP request in Node? Well, it's actually very easy. When a request comes in, okay, this comes in at the big to do synchronous processing, and then it's typically it idles when it needs to call the database, and then when it finishes, it sends the request out in another block of synchronous processing. Okay, so basically we have 2 blocks of synchronous processing and 1 block of asynchronous wait. Seems reasonable, right? Good. So I hope you like some maths, because this is what we are doing. So in here you have, if you consider this, you have essentially 2 units of synchronous processing plus 1 unit of asynchronous processing. So this means that if you want to compute the total response time, the total latency, it's around 30 milliseconds. Why? Well, because you have 10 milliseconds to process, 10 milliseconds to wait, 10 milliseconds to process, 30 milliseconds of total latency. Is it good or bad? Whatever. So, in theory, given all this math, the total number of requests that is serviceable in 1 second by one single CPU is 50, okay? And you can run the math yourself, but basically you don't need to consider the I/O wait because of what we said of the event loop. So we can process, if we have a request that's 20 milliseconds of synchronous processing time, we can only do 50 requests per second. Consider what I said, that some of the node service can do 20,000, 30,000. So the actual amount might be way, way lower here, down to, 1 millisecond or something like that. Cool. Well, what we're going to talk about is denial of service attack. So be careful on what you do and what you wish for. Okay. So the question is, what happens when a lot of requests arrives all at the same time? Okay. So what happens if a lot of requests all arrive at the same time? And is it a problem? Does it work? Can we actually do the things? Well, let's do a little bit of simulation maths and so on. So let's say that 3 requests arrive at the same time, and we can extend this model to 50 or 100 or whatever. And so what we can do is we have a request coming in, and this goes to synchronous processing, synchronous processing to the database. Okay. Then after it's done that, the database processes the things. Okay. Now, we receive the first request, which is green. Okay, you can see the green one here that goes to the database. Then there is the yellow. The yellow can be the yellow request can be the synchronous processing can be done after the green. Okay, so we do the yellow here. In between, we have received the request, the response from the green one, but we still have the red one to process. So this comes first because it was arrived earlier. And so it goes in here, and we got the red one, okay, which scheduled the third request. Now, after all of this is done, we can start replying to the first one we received, which is the green goes out, the yellow goes out, and the red goes out. What's the total response time of the last one? That's the question for all of you. Now, let me run the math. So the response time is 2 synchronous processing unit plus 1 asynchronous processing unit, with 10 synchronous processing unit, 10 milliseconds for each synchronous processing unit, and 10 milliseconds of I/O wait. So considering the diagram we did, the first one will do 30 milliseconds, the second one will do 50 milliseconds, the third one will do 70 milliseconds. Wait a second. We have been receiving a lot of requests running at the same time. All of 3 arrive at the same time. The first has a latency of 30 milliseconds, the last one has a latency of 70. Who? And what if we scale this up to a lot of requests? Okay, well, there is actually a formula, okay, which is, it's not a nice formula because it has a few, it's not a really nice formula, okay, because it scales badly here. And we can see that in a second, okay? So, So this is actually pretty good because with 50 requests per second, we can actually get a lot done, and we can keep our response time pretty nice. Now the problem here starts when we go over what we can handle, because at any given second that passes, we accumulate more delay. So this is the delay; it's not the response time. This is the title is wrong. Okay, this is the delay, the delay total. So and here we don't, you see, it's growing badly, okay, and it's yes, we are building a lot of delay, and if we double it, it even goes to whatever. So it's actually, we need to slow things down and apply some back pressure to our system so that we can handle all those requests coming in at the same time without destroying everything. Somebody might say that scaling the CPU usage is enough. Well, first of all, scaling, it has its limits, okay? The autoscaler needs to kick in, and you need to monitor it. The second problem is, ultimately, you can have 100% of utilization and still have capacity left in your system, okay? So why is that? Well, Node.js runs on multiple threads. So it has the garbage collector typically runs on a separate thread. The CPU optimizer runs on a separate thread. Then there are threads for file system operation and a lot of other things. So the result is you can have a lot of free CPU cycles to use before it slows down. So, and you still don't want to scale too early. So, well, part of this comes also from the nature of the event loop, okay? So you need to always keep in mind that the event loop dominates all of this. All of this. So in the most important phase is poll, and poll allows you to, is where we got new requests coming in, okay, which is nice. And so we can, and then there is timers, okay. Timers allows us to monitor the event loop if we want to, because we can essentially schedule, oh sorry, it went somewhere. We can schedule some data, a timer to kick in, and if there is no connection and data coming in, then the timer will be kicked. We will see the timer coming. So that is actually a very good way to know that our event loop is idle. Now, how can we measure the timer, the event loop? It's actually very good because you can have the set interval and just check between the last time that the interval was supposed to fire versus the time that it actually fired. And then you can measure the event loop delay. So you can say specify, you have the time it was done, okay, plus minus the begins and stuff. It's great, okay. And then you can say if you have over a limit of 1 second, you can say over a limit, whatever. You can check how much delay you have in your event loop system. However, because of this nature of the event loop, as you can see, only fires if we can only measure after we are clogged, okay? We can only measure the event loop delay after we are really clogged, and there are, in certain cases, that might not even fire ever or something like that. So it's a little bit of problematic, okay? It's really good at mitigating incidents, but, not so much at preventing problems. So, yeah. I've talked a little bit about the multi-threaded thing before. So in the something very useful to note is this article from a Node source, which introduced the ELU. I love ELU. Okay, ELU is it's fun. It's very important. And sorry, why does this keep moving? And it shows it's a model to monitor the amount of time that is spent in the event loop, that is spent in the event loop utilizing the CPU, and it's a metric that we can read straight from libuv, essentially. What does it mean? Well, we can actually have a metric that tells us we are using, 80% of the current capacity in the system, or 70% to handle events, okay, or 80 or 90, 98, whatever. It's great. How does it work? Well, it's actually very simple. You just, similar to before, you can call it in an interval, and we can just call the event loop utilization on webhooks, on perfhooks, and it works perfectly. And you just computed the difference between the two, and bang, 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 and you get this number that is essentially a percentage between 0 and 1, and tells us how much of the event loop was used. Okay, so since last time. So you can say if it's 1, you have you are full capacity. Okay, there is nothing left in the system to do anything. Okay, but with this measure, we know when it's going to kick in, when the event loop is kicking in before it happens. So it's great. So you probably all know that I built Fastify a few years back, and so we are talking about how to use this in Fastify. So, well, in Fastify, we have a nice module called Under Pressure that you can use, and you can specify the max event loop delay. You can also specify the memory and the event loop utilization, okay? And that's it. You don't have to do anything else. It's all automatically set up for you. Works very well. How does it work in practice? So what it does, you receive the 3 requests. After a while, the event loop utilization goes at limit, over limit. And then what it happens is that any further request that comes in gets an immediate response, a synchronous response, returning a status code 503. What does this mean? Why is this important? Imagine that you have you have accumulated, I don't know, 2-3 seconds of delay, okay? A user will not wait for those 2-3 seconds, okay? You can just return something. You can just return a 503, return an error. This server is not going to come to this request. Your load balancer typically receives that 503 and can potentially kick in a scaling request to your autoscaler or your Kubernetes or whatever you're using to get the things going. And it's actually a very good and very neat solution to implement also the status code, the else checks. Okay. Now, it's very nice. Okay. Well, it's demo time. Okay. So let's see if the demo gods are with me and if I can show it if I can show it correctly. So let's do in code. Okay. Here we have our first is our server, okay? So and let's vim the server. So it's the server. You see that it just import a route, and the route is here. We use this module called atomic sleep to simulate a synchronous. So there is sleep and atomic sleep. Sleep is an asynchronous activity, and atomic sleep is synchronous work. Okay. So we run it and we do node server. And then we do a short demo. So here we have the we have a demo command. We do 50 connection for 10 seconds. Okay, you will need more to actually appreciate exactly what's happening, but you can give you an idea of what is going on here. And we set it up with a timeout of 1. Okay, what does this mean? It means that we cut the connection at 1 second. Reality, it might be 2 or 3, but end users will go away. What does it happen with this case? Okay, sorry, you probably are not seeing it. Okay, you're probably now seeing it correctly. So you see what we are seeing is that with 50 connections, we are the latency. It's the 99th percentile is at 1 second straight. Okay. Because look at the math that we've done earlier than that, the 50 millisecond and so on and so forth. Remember the math, and 99% latency is at 1 second. And then dash T, and because then it gets truncated. So yay. And that's kind of it. And we do very little requests per second. Okay. Really, the average is 4. Okay. Like it's nothing. Like this is very bad. Okay. So how do we do things with the protection? Okay, so with the protection, we just add the under pressure module, and we say that we event loop delay 200 and the max event loop at 80%. Okay, so what this means, if we do node server protected, and we run the same command, this is the moment of truth. The silence kills me. Now you can see that we get a lot of requests, a lot more requests. Okay, we are hammering the server. Okay, we have, if we consider that before we got only 40 successful requests, now we got 163 successful responses in the same 10 seconds. Which seems a lot more, okay? We also got quite a lot of 503 responses saying that, no, this system cannot handle. And also the latency, it's super short, okay? The latency is great, okay? We also got a few timeouts because that's at the beginning of the system when it's when the circuit breaker clicks in, okay? And in fact, you can see that you have a max latency of 999, something like that here. So those are those timeouts things. Okay, so but can we do anything better? Okay, yes, we can. In fact, there is another mode called a big load aware, and if it's load aware, it's really good because we can even ask the server, is the server under pressure? Okay. And then if it's not under pressure, we do the hard stuff. If it's not, we don't. Now, this is fundamental. This is phenomenal because we can actually decide on what our request is going to be handled by the amount of traffic that the server has. So, so we run it, and now we can run our demo. Okay. Because the node itself is self-aware of its status, we can decide to return them some very good results very early. And now you can see that the numbers here are fantastic, okay? Fantastic. Because we can do quite a lot more requests per second. The latency is very low. What we trade, we can serve, I don't know, some potentially stale data, cache data, data that is not super ready, something like that. And I like that idea a lot. This is actually super good because it's performant and we can do all the stuff. Now, what would be fantastic is if your nice server-side rendering pipeline would do that for you, and for React and stuff like that. So, you know, hopefully one day I'm very positive. That React and Next will do something in this regard. This seems pretty cool. Yes, you can serve the cache instead of a 500 response. Okay, so essentially you're trading. I'm sending stale data versus sending stale data instead of sending an error, which seems better from my point of view, but it depends on your app essentially. But it can help navigate hard times. Okay, in here you can help navigate hard pressure times, and you can handle a lot more traffic with same amount of resources, even if it spikes, which is great. Okay, so let's go back to the demo gods. Okay, I thought the demo gods were with me. I'm very happy. So other techniques to not block the event loop: move all synchronous processing outside the event loop. Okay, the main event loop use worker threads. Worker threads are the nice have a nice have nice APIs so that you can even check how many, especially Piscina. Piscina is a worker pool implementation, and you can even ask how many jobs are queuing to be processed. Therefore, it's fantastic for that because you can, you know, you don't need to, you can actually have a much tighter control on what's going on that. Also, you can even decide to deduplicate asynchronous calls, okay, and the synchronous processing that follows. So, and this is using this module called async cache dedupe that I cover in my other video, the how to make your API 5x faster, something like that. That is on YouTube as well. And here you have the with that module, you have 3 requests coming in at the same time, and they duplicated. So only one goes to the database and gets processed. And then with the data that is getting generated, we can respond to all of them. This is fantastic because, in fact, here we have removed the kind of the biggest problem of the previous of the architecture at the beginning, which was having to process the data for all of them. Okay, now we can, cross the stream, and do the stuff. And just respond once. So that is a great technique to even improve more the performance of your app. How do you do it? It's very easy to set up. So you create a cache. You can even specify Redis here. You have both a TTL, you can set it to 0, and a stale flag. The TTL governs how long the data is valid. Stale governs how long after the TTL is expired, how long to keep serving data while fetching something new. So in that way, you can still you can almost fetch everything from memory all the time, and it's great. So and something very cool is all of this is built inside Platformatic, so you don't need to worry about it. It's already built in set up, so you can easily get to it. And I really love this slide because Platformatic helps you move from A to B like with a high-speed train. But then there is a very nice and small electric SUV to move it to C because, nobody lives near the station. So, thank you very much for watching this talk, and see you next time.